In this video, we're going to talk about weak acids, weak bases, conjugate pairs, which are a special pair of acid and base. We're going to go over equilibrium values with this, so Ka, Kb, acid and base dissociation constant. We're going to talk about something called Kw, which is the dissociation constant for a reaction involving water. And we'll go over how kind of all the math works. I'm going to say the specific calculation portion again for in class. This is just kind of to get the notes in your notebook. We talked in the previous video about how a strong acid and a strong base are substances that dissociate completely, and I gave you the list of the 6 strong acids as well as the strong bases. Well, if a strong acid or strong base dissociates completely, weak substances do not. They only dissociate partly in water. Right now, again, like I said for strong bases, how you can have something like calcium hydroxide, which isn't very soluble, but still be a strong base because it completely breaks up. You can have substances that are extremely soluble, right? So, for example, acetic acid is very soluble in water, but it's still a weak base because it doesn't ionize completely. Now, in order to determine how strong an acid or a base is, we look at their acid equilibrium constants, so Ka or Kb, and even a more shortcut way to do it is look at what's called pKa and pKb, and we'll get into those in a few minutes. Right, so Ka and Kb are going to be huge here. Right, so for a weak acid, for generic weak acid, our acid reacts with water, forms A- and H3O+. This reacting with water has not changed significantly. The only major difference is that because it's a weak acid instead of a strong acid, I use the reversible reaction arrow. Right? Strong acids go to completion, weak acids do not. Our acid equilibrium constant, once we have the equation, easy enough to write, products over reactants. And the math works just like it worked when we were working with equilibrium problems. Normal ice table rules apply. Very, very straightforward to work with. Now, we can take another p-value. So we had pH, we had pOH. Those were based on the concentrations of H3O+ and OH- respectively. We can now work with a value called pKa, which is just the negative log of the acid dissociation constant. The key thing about pKa is that lower pKa's mean stronger acid. Right, so the lower the pKa, the stronger the acid is, just like pH. The lower the pH, the more acidic the solution. Right? Then we have weak bases. Again, same thing as we were talking about bases in the previous video. Only change we made here is we're using the equilibrium arrow because this reaction does not go 100% to completion. Right? Kb expression works the same as we would expect it to. Just one small little thing I have to put in here is I forgot the brackets around our base because this is a concentration. And similar to pKa, you can tell the strength of a base by its pKb. The lower the pKb, the stronger the base. But that's not the key thing to take away from this video because we've done tons of equilibrium math by this point. The key thing to take away from this video is we're going to talk about what are called conjugate pairs. Right? Whenever you have an acid react with a base, that reaction actually contains 2 acids and 2 bases. Right? So let's talk about reacting acetic acid with water. We put acetic acid in water, we form the acetate ion and the hydronium ion. Acetic acid is obviously our acid because it's losing a proton to get from H+ over to acetate. Water in this case is going to be our base. Now on this side of the equation, the reversible reaction, going back the other way, hydronium is our acid because it gives up the proton, and acetate is our base. And if you remember a worksheet you may have done sophomore year, you took this, you drew an arrow from here over, labeled it as H+, took an arrow from here over, labeled that as H+, showing the transfer of the proton between the acid and the base. Same exact thing applies, right? So we have 2 acids and we have 2 bases. Now we pair these up into what are called conjugate pairs. Conjugate pairs only differ by a single H+. right? So acetate and acetic acid are a conjugate pair. Here is our acid. This is the conjugate base. Water and H3O plus are another conjugate pair. Water was the base. H3O plus is its conjugate acid. They always get paired like this, right? So each side of the reaction will have one acid, one base, and you can further pair them up by conjugates. Conjugates become exceptionally important when we start talking about buffer systems, which is going to be in the next section of this unit, right? Because buffer solutions are made up of conjugate pairs. One thing that may be kind of useful for us is to kind of relate the strength of a conjugate pair. In general, the stronger a substance is, the weaker its conjugate's going to be, right? So for example, if we take perchloric acid is one of the strongest acids in existence. Its conjugate base is the perchlorate ion, right? So this is a strong acid, a very strong acid. This is a very, very weak base. It's so weak, in fact, that we just say that it is negligible. The reason why is because since perchloric acid completely dissociates, there is little to no chance that perchlorate is going to undergo the reverse reaction and pick that proton back up. Right? So strong acid, negligible conjugate base. Now, if we move down the table a little bit, if we look at, for example, phosphoric acid. Phosphoric acid is a moderately strong acid, right? It's relatively high on the acid strength list. Its conjugate base, which is dihydrogen phosphate, taking away one of the protons, is a fairly weak base. Stronger acid, weaker base. If I go down to, let's say, hydrogen carbonate's a very weak acid. But the carbonate ion is a significantly stronger base. We're not saying it's a strong base by definition, but it's a stronger base than carbonate or hydrogen carbonate is strong as an acid, right? So that's something you should keep in mind when we start talking about acid and base conjugates, is the relative strengths involved, and you can kind of break these ions up, their conjugate ions, into acidic ions, basic ions, and neutral ions, which are the ones that are generally negligible. Right, that's one way we can look at our acid-base reactions coming out a little bit later. A substance is amphoteric, also called amphiprotic, if it can react as an acid or a base, depending on what it reacts with. Right, so water is the classic example. If you pair water with a fairly strong base, water will act as an acid. If you pair water with a strong acid, it will act as a base. And to finish off, we'll start talking a little bit about the special reaction water has with itself called autoionization. When you get two water molecules together, about 1 in every 10 million or so will donate a proton to another water molecule, forming H3O plus and OH minus. We actually have an equilibrium constant for this reaction. It's called Kw, so equilibrium constant of water, I should say. And at 25 degrees, it's 1 times 10 to the minus 14. Now, the key thing about this autoionization reaction is it gives us a way to relate a lot of different things to each other, right? So the equilibrium constant of water, Kw, is equal to any substance's Ka times its conjugate substance's Kb. It's also equal to the concentration of hydronium times hydroxide. It's also equal to the pH plus the pOH, or the pKa of the acid plus the pKb of its conjugate base. Right? So using this equation right here, I can tell you one piece of information about one substance, and you can figure everything else out about it fairly straightforwardly, right? So we're going to spend a decent amount of time in class practicing with all these different calculations and working back and forth through them.